Enquiry-based learning with Debbie. Please, as ever, do put something in the chat box so we know you can hear us. Let us know where you are, and any observations, questions, or that you'd like us to address from the 2 sessions before. Hello, St. Lucia. Thank you so much. It's great to see you here, and Trinidad as well. That's fantastic. And Antigua, oh, fabulous. Great representation across the Caribbean. Thank you all very much indeed. Oh, that's so good. Loads of them coming through. Thank you, Debbie, for 2 fabulous days. And what I know, having seen the presentation, is going to be a great way to end this session on inquiry-based learning. If you've joined us for 3 days, there is a special certificate that is coming to you with your name saying that you have now spent 3 hours learning inquiry-based learning. And as ever, the recordings and all the presentations will be sent to you as well. Do use the chat box. Do ask Debbie lots of questions because she loves to engage with you. Debbie is an expert in inquiry-based learning and also an expert in science, along with other subjects as well. But Debbie, I'm going to hand over to you for this session, and thank you very much for giving up your time, everyone.
Hello, everyone. Oh, this is so nice. I was just saying to Amanda that because we've done 3 days in a row, I feel like it's almost like we have had a little conference. We have been together like we would in the past. So this is great. And it's lovely to see people from yesterday. Rihanna, Frederick, thank you so much. 30 degrees there. It's 9.5 here, but at least it stopped raining because it's been raining all day. And it was snowing a couple of days ago, so that's good. So it's great to see you all coming back and the positivity. It's really lovely. And your comments last night honestly blew me away. They really did. It's so nice to know that I'm very conscious that you're giving up your time, your valuable time, and I know how valuable teachers' time is. So to give up 3 days in a row, it's so lovely. And I'm so conscious that I want to make this worthwhile, a worthy use of your time. And the comments last night were just amazing. And I cannot thank you enough. That was praise indeed from a group of professionals that I respect incredibly. So, yeah, a compliment, massive. Thank you. So, hello, lovely comments coming in there. So, again, like yesterday, please, any questions, just stop me. As I said, you get these presentations, so you won't miss out on anything. If we don't look at any of the slides, you won't miss anything because you've still got all that information. So we'll be looking today at the properties and uses of materials. And again, that's because I've been asked to cover that content, but we will be looking at it again from inquiry-based learning. So if nothing else, it'll be great if you left these sessions with a really good, firm understanding of inquiry-based learning and a confidence to be able to change and adapt and apply your resources that you've already got to inquiry-based. We don't have to rush around buying lots of equipment and new things to promote inquiry-based learning. And if you leave with nothing else but that and a few ideas, then we've achieved something this evening or the last 3 evenings together. So good afternoon. We've got Melissa, Ronaldo. Thank you so much. I hope you enjoy this. We've got really good coverage of the Caribbean here. Jamaica, Tobago, Grenadines. It's amazing. Fantastic. Belize. Let's move on then. I could sit there looking at your comments all night. I don't think you'd be very pleased if I did that. So we are looking at inquiry-based learning. We want to be confident. We want to be confident planners, deliverers. We want to be experts in inquiry-based learning. We know why. We have no choice really. We need to focus on the skills. But we're also looking at the properties of materials, the uses, and some investigations, the reasoning behind why it's so important that students are confident about what the property of a material is and why we use certain materials for certain objects and tools because of the properties. So let's have a little test for those of us who've been here more than once this week. Let me see how many of you, because you're so good at engaging with the chat box. I can do interactive things like this. So let's see how much of this you can remember. So, knowledge without understanding is what adjective would you use to describe knowledge without, yay, ran out again. Frederick, I love that. Meaningless, useless, sterile. This is my day 3. Well done. It's my day 3 too, so well done. Useless, sterile, meaningless, useless, no point to it at all. Okay, so why do we use it? What do we use it for? What's its main use? It's only used for, come on, Frederick, you know this. Recall and assessment. Yeah, that's what we discussed. We said initially recall, but you know what? It is just to assess. Now, because we know each other quite well now, I can say this. One of my students who was much older, he was 13, and he actually said to me, why do we need to learn all this stuff? And I said, well, because it's how we measure your understanding and how you work and the skills that you know. And he went, all we do is you throw loads of information at us, and we go into an exam room and we regurgitate it onto a piece of paper. We come out and we forget it. And that's in my early days, and I thought, no, this is not what being at school should be like. So understanding then goes where? Why is understanding so important? Because understanding goes to, come on, Charmaine, you know this, to memory. Yeah, that's true. And before that, it goes to a much, 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 much deeper intellectual level. So it arrives, it makes us get to such a deep intellectual level of understanding that we can transport it safely into our long-term memory. Yep, synthesizing, applying, all those higher levels in Bloom's, the ones where we get the intellects, the ones where we get the academics, that's what it leads to. So it enables students to think and apply, to synthesize, to think, apply. So there you have it for your own use when you can share with your colleagues and test them. So I think you passed that test. Well done. Good afternoon from Jamaica. Okay, so what is inquiry-based learning? I would be testing you now. It's about encouraging learners to question. Questioning is at the heart. We want them to learn the skills. Why do we want them to learn the skills? Why is learning skills always important? Why should skills be driving learning? Because the cross-curricular skills, the lifelong cross-curricular skills, it's not just about science, it's not called science inquiry. Some people call it science inquiry, but it's not. It's actually inquiry. It's cross-curricular, it's directed at any age. You don't have to be a certain age to be able to engage with it. It's for everyone and it's lifelong. And as I've said before, if you're teaching 7-year-olds, 4-year-olds, 40-year-olds, 19-year-olds, whenever you're teaching them inquiry-based skills, you are teaching them skills that will be with them for the rest of their lives. The content, they will use it until the next level of that content. Yeah, it's a foundation, but they'll continuously progress and go into new areas, new fields. So it's about the skills really that drive the learning. We need these skills. We need them more than ever because we're playing catch up, as we've said before. We're trying to catch up. We're trying to get the children where we want them to be. We're professionals. We've known where they should be. We've taught before, and we're thinking, oh my gosh, it's April, and last year, 2 years ago, the children were in different places educationally, and so we are in a little bit. We're under a lot of pressure and a lot of stress to get the children to where we think they should be. And don't forget, they pick up on that pressure and that stress. And so we can't afford not to develop inquiry-based skills, because they need to take responsibility for their own learning, and they need to use their skills effectively to learn independently, because it's impossible to cover everything and to catch up. And as I've said 1,000 times, and I'll continue saying it, I'm not sure who we're catching up to because we're all in the same place. We're all not where we were a few years ago. And so I'm really not sure what we're catching up, but I do understand that you're under a lot of pressure to get the children to where you want them to be. So how do we teach children to learn how to learn? They've got to have a high level of self-organisation, resilience. They need to work independently, but yet collaborate and work as a team or a group. I was reading some research yesterday about the value of group work and teamwork, and how it develops so many skills that we're not even, as a classroom teacher, not even really aware of, because we're teaching, we're on that journey with them, and we're trying to get to this destination. But actually, the research is now telling us that the group work teaches so many things, such as being a team leader, managing emotions, being aware of our own emotions and controlling them because we're in a group situation, being aware of spontaneous actions such as snatching, interrupting people, all these things that when you're in an interview really, really impress the interviewer, and they're developed through group work almost subconsciously. So we're teaching all these things in inquiry-based learning, and remember, learning is an alteration of the long-term memory. If it's not altered, if memory is not altered, no learning has taken place. And the amount of times that teachers say to me, I've taught all the curriculum, and I say, wow, you've taught it, you've got through all that so quickly. And they say, yes, I have. And I say, and how much have they learned? Because really, we're better teaching the skills and them understanding to that deeper intellectual level some parts of the curriculum and none of other parts. Better that than fly through the whole thing and none of it gets into the long-term memory because of the sheer speed that you're working at. Skills promote and build confidence, absolutely. Not just confidence in that subject area, but confidence as a person and as a learner. That is so true. I was observing some primary school children a couple of weeks ago, and we were trying to encourage them to aware of their movements and aware of people around them. And inquiry-based teaching and learning encourages that movement, doesn't it? We encourage them to go and speak to other groups of children. We encourage them to speak to others, and that builds confidence. It builds confidence in communication skills, moving around, and being an effective student. So you're absolutely right. It does build confidence. So don't forget these skills. And if you want to change any of these skills and say, well, I think that one's not a skill that should be in this top list, I think other skills should be there, please drop me a line, because I'm always interested in, you're in the classroom all of the time, so you are more aware of the skills that your children need. And so when I was in face-to-face meetings all the time, I constantly used to change this skills list. I used to say, I just steal ideas from you people, from you teachers, and I call that sharing good practice, obviously. But yes, this list used to change all the time, and now it doesn't really change very often at all. So in the resources that I've written, I like to include tasks and activities that are always guided at least one skill and often several skills. Hi Leah from Trinidad and Tobago, how are you? I hope you're okay and had a good day in school. So here we've got a research task, so we're asking them. And sometimes, as I said before, teachers will say to me, yeah, but we haven't done that, because that's the synthesis part. But it's not just synthesis, is it? It's about developing research skills. Can they actually analyse the research information that they've found? Can they weigh it up if that's reliable? Is it good? Is it a good piece of information? Has it been properly researched? Does it come from a good source? And is it current? And so by doing these tasks, we're not just asking them about cutting down trees, but we're actually developing the other skills as well. Plus, how will they communicate that information back? To what audience? So often when teachers are asking questions, I will say, what answer are you looking for? Who are you asking the question of? How will you ask the question? How will they communicate the answer? Can you see that, like inquiry-based learning, we're given tasks, but it's not the actual task outcome. It's the skills that we use to get there that are important in inquiry-based teaching and learning. So when we're asking questions, for example, the important part is why, who, how, and what will you do with the answer? What are you looking for, and what happens if you don't get that answer? Where will you go? How will that affect your planning? There's another challenge that I like to throw challenges in there, and I like to say things like a song or a poem, because it detracts away from the content a little bit. And some children really like composing songs and poems, but also we now know that research is telling us that when we're revising, if we can put content to music, it actually helps us to recall information accurately. So using songs and poems is actually, whoa, scary to me, because that is not my forte, but I can understand that some children would really enjoy that instead of writing a script or writing a sentence or something to communicate their ideas back. So how do we get them to ask questions? Because we want them to ask questions. Remember, questions are at the heart of inquiry-based learning. If you develop and design a good question, that's great. But if that's all you do, that's not so great, because when they ask questions, that's powerful. If you remember, the reason that that is powerful is because that shows they're curious, they're interested, they're engaged. If they ask a question, they will work hard to find the answer. If we ask a question, some of them don't even want to answer it because they don't want to be the centre stage in the classroom. Some of them are not confident, and so they don't actually want to verbalise or communicate an answer. But we want them to be so interested and engaged that they're asking questions for themselves. They want to know. And when we're at that point, that's success, because that leads to deeper intellectual understanding. So it directly transports the information into the long-term memory, and it's accurate and useful information. I call this agenda building. These pages here show photographs that we hope will get the children interested and want to know about this. Why is the popcorn on that page? Why are there eggs on that page? A raw egg and a cooked egg? Why? What's the point in that? So in planning, there must be a variety of differentiation displayed to engage the audiences. It depends what audience you've got, and you know your children, so you know these things. My students I used to have classes with lots of boys, and I'm not saying there's anything wrong with that, but they used to get disengaged very easily. They wanted to be active and doing things. And if I brought something in that was gory, like a human heart, not a human heart, a pig's heart or a cow's heart, or if I brought in some eyeballs and threw them across the room and they stuck to the wall, they used to love it, because that's what they were interested in. Knowing your students and knowing what they're interested in actually means that you can play to their strengths, you can play to their interests, and it's easier to engage them. So we've got questions the students ask are based on their curiosity and thirst for knowledge. I find that stories associated with a topic helps trigger their curiosity. For example, why are there so many plastic bottles on the beach? How will this affect wildlife? Where did it come from? Yep, great. That's absolutely perfect. And I know a lot of younger children do love to hear a story. In fact, when I'm teaching in early years, which is before primary, I always link every single lesson or a group of lessons to a story, because it is a great way to engage. Some people use music. We can use activities. We can have just pictures like this. Now, these are from my book, so obviously there will be pictures. I can't put music in a book, so you understand that. But also, let's remind ourselves the talking points are not assessment questions. The questions to stimulate discussion, because in inquiry-based learning, what we really want to arrive at is discussions. We want the children to be talking about the science, because then we can listen and we can hear their ideas, we can hear prior knowledge, and we can hear misconceptions, and we can deal with them immediately. And so we want discussions. So these talking points are not assessment questions. And many teachers have said to me, but how would they know that? We've not started teaching it yet. You'd be surprised how many times do we get surprised when children say something and we think, wow, how did you know that? They know much more than we think they know, and they know much more than they think they know. And so listening to these discussions is really valuable in an inquiry-based learning. It is one of the things that we direct. It's very important that we get these discussions. Some children might not be interested in those pictures, but they might be interested in the fascinating facts. Remember also that whenever I write, wherever I can, I try to link it to real world science, and science that's taking place in the places where I'm writing books for. So in these books, you'll find that there are lots of Caribbean scientists that are not just from the Caribbean, but they're working and living in the Caribbean, because I don't want students to think that science is something that's far off and magical and they can't possibly engage with. And I always tell students, I say, what is a scientist? And they go, oh, well, it's somebody who wears a white coat and they do all these experiments. And I say, and have you ever met a scientist? No. And I say, well, you're scientists. We're studying science, so we are all scientists. And they look at me like I'm a little bit crazy, but it's the truth. If you're studying science, you're a scientist. And so I want them to see that it's a career that's available to them, and it's not something far off and impossible. So in this, we're looking at the properties of materials. So we're starting to build on some prior knowledge that we learn in year 4 and before that, really. So we're looking at that foundation that we're building in primary science, and we're building on as we progress through primary. So I was asked to look specifically at the properties, which are later on, really, in year 6. But even so, I wanted to look at it. If a child asked me about properties, I would talk about it from the age that they're at. So I would never ignore it and think, well, they're too young to know that. That's pointless. We want to do it when they ask. So one of the things I use early on are things like this. I like to use little pom-poms. One, because they're cheap. Two, because they last forever, really. I've had these years. And you can get them in different shapes, sizes. And children often quite like to play and manipulate them because they've got a great texture, they feel good, they look good, different colours, and I ask them to sort them. And initially they will sort them into the colours, so they'll have all the pinks, all the reds, all the whites together. And then I'll say, is that a good way to sort materials? Is colour a property? And the answer is, in science, no, it's not. Colour is not a property. And so we need to move away from colour, really. And so, but we can sort them in different ways. So I like to use a straw. If the children haven't got any breathing difficulties, I like to put them in a pot and get them to separate the pom-poms using a straw. It slows them down. It's good fun. It's a giggle, and it makes them really think about it, because they might actually all go for the smaller ones, and then they realise that some of the smaller ones are really quite dense and some of the bigger ones are really not dense. And so often the smaller ones actually they're harder to suck with the straw than some of the bigger ones. And so that can be quite good fun as well. And it's just better than sorting things out. And then we bring it in. Why is colour not a property? Well, because you can have a pink helicopter and you can have a pink feather, and they're very different, and you wouldn't use the same materials to make either. So colour is not a property, not a scientific property. So then we move on to what are them. So we start to talk about classification, and classification is a scientific skill. And so we talk about how we can sort. It's more complex than sorting. So you've just grouped and sorted those pom-poms into different colour. Now we want to classify them. So how can we classify them? Well, we could classify them from texture, from mass, from how squishy they are, how elastic they are, how flexible they are, different, more formal types of scientific classification. We can look at stretchy materials. So I've got various different things. As you know, I do not like spending money on resources. And so I've got resources that are all falling to pieces. Excuse me. I've got resources where we can use paper clips and elastic bands and a ruler and a bag with some coins in, and basically we can look at elasticity. So we can get a range of elastic bands. I've got a paper clip that I've unfolded so it becomes a hook. I then can measure the length of my elastic band with just the hook on it. That would make it more of a fair test because we're keeping the hook on all the time. And that's 23 centimetres. So we're measuring. It's not easy measuring either. It's quite difficult to measure an elastic band. We're thinking about a fair test, so we're keeping the hook the same. We'll attach, this is just a bag that's got tie handles on it and some coins. And then I will measure my elastic band, and it's now, if I get the elastic band the right way around, it is now almost doubled in length. And we can keep adding coins, pebbles, whatever you've got available, weights if you've got them, until it either breaks, which they often do, or, which is good fun, if it's done safely, or it just stops stretching because it's reached its capacity. So then we can talk about recording results. We can make a table of results to record that. We can talk about why does it stop stretching? Because it's reached, it can't stretch anymore. That's it. Just before something breaks, it comes to breaking point. It stays there for a little while and then snaps. So there is a point. So that's also interesting. You can balance the hook between on a pencil or something, between two desks, between two stacks of books. Lots of different ways to do it, but we can talk about fair testing, how stretchy a material is, and the importance of the property of stretching or being able to stretch out and then return to its original shape. Why is that important? Ask them how they would put a sweatshirt on, or a shirt, a pair of socks, a pair of gloves. How would they put all these things on if materials were not stretchy? It'd be very difficult to wear a t-shirt that was made out of glass. It would be very difficult to wear a t-shirt made out of wood. That flexibility helps us to use the material for much more products. And we use it specifically because of the elasticity. Teaching elasticity again, when we've just done that investigation with the elastic band, compare it to different sizes to prove again that the colour is not a property. You could say, okay, test which one of these is the most stretchy. And we'd like to think that, oh, well, that's not fair, miss, because the different colours are, say, and let them explore it, and they'll realise that actually they're all from the same pack of elastic bands, and so they're probably all the same, will stretch all the same, and so the colour actually doesn't affect it at all. And so that reinforces the idea that colour is not a property. And then I also like to do another stretching exercise. I can sometimes teach students who fiddle with things. Well, this is a great thing to make. It's investigating stretching. It's also practicing manipulating small objects and the pincer grip when pulling the elastic. It's competitive, it's great fun. We start off by just a knot of an elastic band, and you just wrap them round as big as you can. Get them to research how big they are. You'll be amazed how big the biggest one is. Let them take them outside. Do they bounce? How high do they bounce? Will they bounce back from the wall? How far can you throw it? How far can you make it bounce away from a wall? It's probably easier to measure than bouncing it up in the air. But bouncy balls are great fun. Probably not this size, because actually these have got quite a lot of mass in them now. And yeah, if that hit you from a good bounce, it would hurt. So be very mindful of how big they are before you take them outside. So that's elasticity or stretchiness, depending what island you're from and what vocabulary you're using at the moment. So why are the properties of a material, how do we find them in the real world? Why is it important? Now, sorting materials and classifying them is actually life-saving, and we can see that from the safety, the labels that are on products. These are international labels. They go beyond language. We all use the same ones everywhere. Some of them are very slightly different, but always clear like these are. And so it is important that we classify materials, because though you would drink a clear liquid that's water, it wouldn't be a good idea to drink a clear liquid that's peroxide. And so it's very safe to use these. Now, we'd expect that in something like a bleach, a cleaning product, that there would be the symbols on there. We'd expect that, because in our mind we know they're dangerous. And so on there, we've got corrosive, we've got dangerous to wildlife, but then we've also got an antiseptic that's actually used on humans and animals and people on wounds. And here, that's flammable. It's actually a flammable product. So we've got a polish, just polish, and that's also flammable. Why am I so interested in this? Because it actually keeps children alive. This is shampoo, and even this has got safety labels on it, and it's shampoo. It's what we use, and it tells me I shouldn't eat it. Now, we'd like to think that all our students would know it's not a good idea to eat shampoo or cleaning products, but it seems a bit, wow, it's a bit shocking that something could be so dangerous. Toothpaste is an alkali. Your stomach has stomach acid. So sorting materials according to their properties keeps us safe as well. And we have to understand the importance of how we dispose of them and how we safely get rid of them, not in the water table. So how can we teach, again, more about materials and their properties using inquiry-based teaching and learning? We've got here measuring. So how do we measure the properties of a material? And we've got some examples there. So we can use a sound level meter to measure the volume of sound in decibels. We can use a clock or a timer to measure time, a ruler to measure length and distance, a thermometer to measure the temperature. We've got scales or top pan scales. We've got a measuring cylinder there to measure the volume and capacity. And we've got a magnet. Now, I get really upset how children and teachers use magnets, I have to say. Sorry, my desk is getting full with equipment as we go. I often get annoyed with students because they will throw magnets around, and when a lesson is happening with magnets, you can hear them dropping and clanging on the desk and on the floor. And I will always say to children, can you break a magnet? And they say, oh no, miss, have you ever felt it? They're really, really hard. You can't break a magnet. No. And then I will show them one that doesn't work. And they're like, why won't it pick this paperclip up? Because it's broken. Why is it broken? Because when you make a magnet, my pin is not magnetic. Because all the domains, all the little particles inside that magnetic material are disordered. Some are facing north, some are facing south, they're facing all over the place. And so it's not magnetic. It doesn't stick to the metal on my glasses. It doesn't pick a paperclip up. It's not magnetic. But I can make it into a magnet by stroking it. And I will watch students going like this, and I don't say anything because it's inquiry-based learning. I let them do that. And I say, oh, is it a magnet now? And they go, no, I told you can't make a magnet, miss. And I said, yeah, but if you're going like that, what are you doing to the little particles inside? What are you doing to the domains? You're mixing them all up. You're mixing them up even more than they were before. So we have to stroke it. And if you do this with a nice big iron nail, you can pick up paper clips. Okay, so that's how to make a magnet. I'm going to stick that back on there so I don't hurt myself. I'm assuming you've all seen the floating magnet. I love this. I never tire of that, I have to say. We can do this using a retort stand, a scientific stand, or we can use it using some of my famous kitchen equipment, a piece of blue tack or modelling clay, stick it to the desk. If you've got some fishing line or fishing wire, it's the nylon thread that's transparent, and you set it up in your classroom with the magnet attached to either a retort stand or on a shelf or something, you can't even see the thread, and so it really does look like it's floating. This is an alternative to children going around the school as well with a magnet saying, oh, that's plastic, it's not magnetic, that's magnetic, that's not magnetic, because it's not attracted to the magnet. This is a nice alternative because you can set up the floating paper clip, and you can actually, the little gap between the paper clip and the, I hope you can see that, the little gap, you can actually slide in pieces of glass, pieces of wood, pieces of paper, card, and if it's magnetic, it'll still be attracted to it, and if it's not, it will fall down. And so they're nice little investigations for magnetism. We can also measure magnetism because there are lots and lots and lots of different types of magnet out there, as you know. So how can we measure which one's the best? So we can show them lots of different ones. Let me see if I can find my array of magnets. Ah, here we are. I collect these from all over the place. I've got a nice one there, a smaller one, if you can see that, a nice little rectangular one. As you can see, I've stolen that from a fridge magnet. Nothing gets thrown away in my house. I've just bought a really, really, really big garage and it's just full of science equipment. And then we've got the standard north-south classroom magnet. And I would say, which one do you think's the strongest magnet? And which one do you think your children would choose? And their early investigations into magnetism, this one. Well, actually, you can use magnetic scales like these, okay? And if you hold the magnet near the display, you'll get a reading. And if you've got a north and a south and you turn it round, you'll get a negative and a positive reading. But we'll not get into that. But they can then, if they've ordered all these different kinds of magnets that you've got in your classroom and they've predicted which ones will be the most, if they've ordered them into their predictions of most magnetic to least magnetic and then they measure it, it's interesting. It's suddenly magnetism becomes a little bit more interesting. And so they're just some activities. I also like getting the trusty box. As you can see behind me, it's always there. It's a shoebox. And you can play tricks. You can put a metal car on the top and put your hand inside the box and make it move. You can make magnetic little stories up using metal characters and things like that, you know, from Small World play and things like that. So you can use magnetism to play lots of games and just explore it in a slightly different way. Students tell me that mass is not a property of air, because honestly, if there was, you'd be able to feel it, wouldn't you? And I go, yeah, I guess you would, that's true. So you're telling me then that this balloon and this balloon have the same mass, is that right? Because the only difference, what is the only difference between this and this? And the only difference is that this one's been blown up. So this one contains air from my lungs. And this one contains nothing. It's deflated. There's nothing in it. It is just the balloon. This one's inflated. So how can I prove it? Well, again, you know me with my expensive scientific equipment. Here's a coat hanger and some string. I'm embarrassed to say I didn't even buy this string. It actually came on a package. So if you get the children to hold it like that, they can see if they've measured the string and it's the same length, the balloon is lower than the deflated balloon. And the only difference is this one's got air in and this one hasn't. So that's a nice little visual hands-on opportunity to think, wow, oh my gosh, yeah, that's a good point, that is. When we're looking at paper and burning paper, again, this is one of my favourite investigations, which for you people who know me, you'll know that it would be one of my favourite investigations because I like burning things. Good idea to do it outside, good idea to do it away from anything flammable, great idea to have some water or an extinguisher handy because one never knows. People say, these are primary school children, they can't do that. My primary school children do. My primary school children toast, what are they called? The sweets, the soft, very sugary, it's gone. But they toast them, so it can be. Marshmallows, thank you, Alicia, thank you, Shalene, saved me there. Yeah, they toast them, so they can if they're trained to do it. There's no point shouting, it's not safe, don't do that, because what will happen? They'll grow up thinking everything's not safe and they can't do it. And then they won't be able to risk assess. So they'll never take any risks. They'll just assume everything's dangerous. Anyway, we burn paper and we say to children, right, measure the mass of the paper using your scales and record it. Key skill. Predict, what do you think will happen when you burn the paper? Will it increase or decrease in mass? Listen to the reasoning because it's very, very, very interesting. Oh, it'll lose mass because it's burnt. Oh, it'll gain mass because it's been on fire. Just listen to what they're saying. And then, okay, for you, your teachers, at your level, actually, it should slightly decrease in mass. They might not actually be able to measure that accurately, but you can go on to say, well, this is one of the flaws in science where our equipment is not accurate enough. But scientists, secondary data, have proven that it reduces slightly because the carbon in the paper, the fuel, joins with the oxygen in the air, otherwise there wouldn't be combustion, and it's released as carbon dioxide and water vapour. So very slightly, though it gains the oxygen, it loses some of the carbon from the paper. So this is one instance where it does actually lose mass. So we're getting into changing materials now. So I like using paper muffin cases because, and you can get some really small ones as well. We were using them last week in a training session, actually, really tiny ones. They were great because you just broke off a little bit of chocolate or a little bit of butter and they were able to float them in hot water. It doesn't have to be boiling. We don't have to bring that hazard and that risk into it. Float it on. And they were measuring how long it would take to start to melt. And that was a great investigation because they were measuring time, they were observing, they were recording, they were predicting, they were finding out all the information, and they were also talking about a fair test. Because is it fair if my paper case is sunk and I need a different one? Or can I get a different one? Well, if it's from the same pack and you're convinced it's identical, yes, but other than that, no. Are all changes permanent? Now, I find this a real difficult one because reversible and irreversible is one of those situations in science where it's been brought down to a simplified level and then it becomes confused. Sticking to chemical reactions and physical reactions is actually easier to explain. Let me give you an example. If you cut up a potato or a banana, is that reversible or irreversible? Well, actually, it's a physical change. So therefore, it's reversible because it's not chemically changed. But that chopped up banana does not look like the original banana. But it is. It is actually reversible. Students can often see that burning something, a firework, setting something on fire is irreversible because the product is different. Baking a cake, the egg going in a cake is chemically changed. It's been heated and it's chemically changed. So it's different. You can't get that back. You can't uncook the egg. So it can be quite complex. And water for me is the best one, because, or chocolate or a lolly or something like that, because you can do it quickly. You can pour the water, you can freeze it, and it melts, especially where you lucky people are. It melts really quickly. Whereas other changes can be quite complicated. So my advice is stick to water, stick to ice cream, make some ice cream. Have you ever made ice cream? I made ice cream with some adults not long ago, and it was an amazing experience. I'll talk about that in a minute. I also once put a peach in a plastic container and put the lid on so it was fixed tight. And I put it on the shelf and I said to the students, how long do you think it will be before it decays? Oh, one day, tomorrow, next week, but certainly a number of days. And we kept looking at it until, I'll be honest, we got bored looking at it. And when I left that school, 9 years later, I found the container on my shelf with the peach in it, and you know what? It looked exactly the same. When I opened it, didn't smell brilliant. Obviously, some air had got in over the years. And when I touched it, it just kind of went like that. But it looked the same. It had actually been such a great container. It was so clean, there wasn't any microorganisms on it, because I'd cleaned it, taken it into a classroom, and it looked like a peach. I could not believe it. And I knew where some of the students worked that had done it, and I actually went to see them and told them they were speechless, absolutely speechless. Okay, I love evaporating and I love making salt solutions. I love making crystals because it's salt and water. That's it. A nice warm windowsill, you can make some brilliant crystals and some great salt solutions. Students often pour loads in and then you don't get a result. I use these, and this is the top from from food packaging with soup actually. And I save things like this, as you know. So I made a really concentrated salt solution, poured some in the bottom. It's not quite perfect, but actually they do make some really lovely crystals. And if you colour the water, 9 years, 9 years was on the shelf. Yeah, if you colour the water, you get some lovely colours as well. And you can puncture holes in, tie them up, put them in the window, and they do sparkle really well. But it's a great way to show that the water's evaporated out and you're left with the salt again. So my idea would be measure the mass of the salt, measure the mass of the water, dissolve it, make sure it's very saturated so the salt's just starting to sink to the bottom and not dissolve anymore. Pour a little bit, a layer, thin layer in on something like this, or a saucer, or anything you've got really. Leave it somewhere nice and warm and sunny. Measure the mass, and you will be able to measure it. It'll be much less because the water's evaporated out and all it's left behind is the original salt. So this should be, if it's a fair test, very accurate and everything's been done right, this mass of the salt should equal the mass of the salt that you made the solution with. But there's so many flaws. But that's interesting because we can talk about that. Is the method wrong? Was it not a fair test? Did we do something wrong? Did we measure it wrong? All those kinds of things. Opens up so many conversations. So there you are, investigating making ice cream. I love doing this. Milk, mix it into a mixture using milk shake powder. Mix it up. Put it into a sealable bag. Put the sealable bag into another sealable bag filled with ice. Pour salt onto the ice to bring the freezing point down lower, because now the salt will reduce the freezing point, and so it'll freeze the milk quicker. The good fun bit is, the funny part, I wish I'd brought the video actually to show you. Then hold the top and you shake it, so that the milk is making constant contact with the ice and the salt, and so it reacts quicker and it solidifies, so it changes state. So you've got the liquid milk, the solid powder milkshake mix, and then it becomes a solid. When you shake it, it makes ice cream. And if you do it in sterile conditions, you can eat it. And yeah, it's pretty nice actually. Lots of my teachers have made that with the children, and it is a really nice activity. And they can see it changing state. That's the beauty of it. When we're boiling water and things like that, unless it's in a clear beaker like on here, and not many people have access to things like a Bunsen burner and a beaker that's heat proof, and we just don't. And this is slowed down to such an extent that you can actually see it changing state. Someone's just saying that you call them milk bags. We just call it ice cream because it makes ice cream, and then we can eat it. And then it melts if you leave it long enough. Okay, so evaporation and condensation. There's another one there where we're actually making clouds. That's part of the water cycle, and that also works. If you get a clear cup, glass, warm water, not boiling, half filled, this one's saying another cup on the top, but I just put the lid of the jam jar on top, put an ice cube on it, and watch as the water vapor rises, and then it starts to cool when it hits the top where the ice cube is, and it forms a cloud. If you can't see the cloud, just get a match, blow it out, and put the smoke into it, because the reason we see lots of clouds is because of the pollution. So we make pollution using the burning matchstick, or if you just slide the top off and spray some deodorant, air spray, air freshener, anything like that, that will also produce a cloud. It's good fun. It's quite safe because you don't use boiling water. You use just warm water. If you use boiling water, it rises so fast it melts the ice cube virtually straight away, and it doesn't work as well. So these are hands-on, minds-on activities that I'm showing to you, because we want the children to be able to explore themselves. Demonstrations have got a great place in science, but it's not hands-on, minds-on learning. Can you see how many skills we're developing here? We're developing the observation, the recording, the predicting, the analysing of results. We're really, really looking and investigating and exploring. And that's what inquiry-based learning is. That's what it is. Remember, observing does not just mean looking. Observing means recording, it means measuring, it means all those other skills. We have also, along with the Mission Science, have developed these workbooks which are right on resources. And this is where the differentiation, I know someone mentioned differentiation earlier on and I skirted past it. And the reason I skirted past it was because I differentiate using things like this. So if you've got students who can't draw a table of results, but they really want to engage in the science, then give them a table of results. If you've got students that want to go off by themselves and investigate and explore, give them the workbook pages so that they can investigate and explore. Also using my coat hanger ideas, if you're looking at mass and weight, there are some great ideas that you can use using a cup. Attach it to both sides, attach a cup to the other side, which I've now thrown on the floor and I cannot reach, and it suddenly becomes a balance. You can add coins or pebbles or anything and it's a balance, so you can see them doing that. if you're doing solids, liquids and gases, if you get hold of some of these, I got these from a pharmacist for giving cough mixture and things to young children. They gave me these because the packaging had broken, so they were no longer sterile, so they couldn't really use them in a medical situation. So I fill the ends with super glue and let it set nice and solid, and then I'll fill one with water, one with sand, and one with just nothing, air. And I let the children explore it for themselves. So rather than just giving them the table that says you can compress air, you can compress a liquid a little bit, you can't really compress a solid, they can explore it for themselves. So that's just using three of these syringes, and I keep these. Once I've made them, I just keep them and just top them up with the water when I want to use them, so we can use them all the time. So that costs nothing, and they go on and on and on and on and on. And I think they are all my resources that I've got. I don't think I've missed anything. I've got a desk full of things here. So that's how we can differentiate. And review. Review is a key inquiry-based skill. We don't practice it. We don't give the children time to practice. This is also, these projects, a synthesis of information. They are where children can just take the information as far as they want to go with it. And lots of review and reflection where children start at the beginning, those conversations with the pictures. What do they already know? And then at the end, review that. Wow, what do I know now? Science is not actually horrible. Science is amazing, I think. So, you've been so interactive this evening. Thank you so much. If anyone has got any questions or anything, I realise we've run out of, well, we've not run out of time. I always keep my sessions on time, so I'm not saying that. But if you've got any questions or any information you want to share, anything at all, please do get in touch, because I really do appreciate it. I miss being in the classroom with you. I miss sharing ideas and having a good play with bits of equipment like this. So thank you so much, and I've really enjoyed these 3 days together. I think we should do it again sometime, because it's really nice seeing the same people attending all 3. So thank you so much. I've really enjoyed it. I hope you have too. So thank you. I'll pass you back over to Amanda. Thank you.
Thank you all. Thank you, Debbie, so much for 3 fabulous days. I think, well, I certainly have learned a lot, and I'm sure everyone else has as well. So thank you for sharing your insights and those wonderful experiments, you can do with all bits and pieces. I mean, it makes me enthusiastic to go and make a sun catcher, I have to say. So thank you, everybody who's joined us. Thank you for giving up your valuable time. As Debbie said, we do honestly know how busy you are, so we really appreciate you spending the last 3 days with us. Or if you've just joined us for one session, then that's fantastic. We will send out to everybody all the resources, so you can share them with colleagues and watch them in your own time as well. If you are if there are any other topics that you would like us to cover in future webinars, then please do email us at caribbean@macmillaneducation.com, and we will do our very best to put these webinars together for you. So thanks again, everyone. Thank you, Debbie, and we look forward to seeing you, maybe even in person at some point in the future.
Yes.
I hope so. Thank you all very much indeed. Bye-bye.
Thank you. Bye-bye.